Today we are going to talk about geocentric parallax and how it affects our observations of solar system bodies. Simply put, parallax is angular movement. You might have seen diagrams like these. If you have two observers who are separated by a separation small d and there is a nearby body at a distance capital D from them, and they are comparing where they see this body compared to stars at infinity, they will notice that the observed position of this body is slightly different for each of these observers. So, for example, if you have one observer looking at the moon and looking at the background stars, they will see these stars in the background, the other observer see these stars in the background. Now, this movement can be due to many different things. You can have the Earth's orbit around the sun, you are looking at stars from different directions, and that is called annual parallax. It could be because of different positions on the Earth, and that is called geocentric parallax. So, let us talk through an example of the moon. Let us say you have this kind of a setup where you have an observer on the surface of the Earth with a radius r, and this is the direction of the zenith. The moon is observed to be at a zenith angle of zeta prime, and the actual zenith angle of the moon, which is calculated from the ephemeris and so on, is zeta. Now, what we want to calculate is the difference between zeta prime and zeta, which we denote as delta zeta, which is the parallax. Now, we are going to denote the distance between the moon and the center of the Earth as capital D, distance between the moon and the observer as d prime. By the sine rule, we know that A by sine A is equal to B by sine B is equal to C by sine C for all triangles, and we are going to use this rule to figure out what these angles are. So, you can write down capital R divided by sine of delta zeta is equal to d prime divided by sine of zeta, right? And if d is much greater than r, this d is much greater than r, then delta zeta will be fairly small and d will be approximately equal to d prime, and you can start substituting these two things to get delta zeta is equal to r sin zeta divided by capital D. So, we can substitute both of these simplifications and we can get delta zeta equal to r sin zeta divided by d. In the next few slides, we will also talk about the problem when capital D is not much greater than r, so we can't use this simplification, which happens very easily for earthbound satellites. So, we note that this parallax makes objects appear away from the zenith towards the horizon. If you observe something at some location, the actual zenith angle is going to be smaller than what you observe. And this is maximum at the horizon, and it changes through the night as the objects rise, transit and set. The correction which you need from geocentric parallax is going to change. For the moon, for example, the maximum shift when it is close to the horizon is about 57 arc minutes. This is huge. This is twice the diameter of the moon itself. What that means is that moonset and moonrise calculations need to be corrected for what you observe as sitting on one location on the Earth versus the center of the Earth. This is also used for measuring distances of solar system objects. So, for example, if you look at the Venus transit, this is Venus transiting across the sun's disk, two observers on Earth can measure position of Venus or measure the time of contact equivalently and figure out what the distance to Venus is. The total offset in this case is about 1 arc minute, which is 1/30th of the size of the sun, and it is fairly easily measurable. This is what was used to set the scale of the solar system. There is a more extreme case where you want to figure out these angles for satellites. So, D is greater than r, but it is not much greater than r. So, we cannot use the simplification that d is equal to d prime or that delta zeta is fairly small. So, in that case, we can still use the sine rule and we can write down r by sine delta zeta is equal to d prime by sine zeta, and which is also equivalent to d divided by sine of this angle, which is pi minus zeta minus delta zeta, or equivalently pi minus zeta prime, the observed zenith angle. We can write down sine of pi minus zeta prime as sine of zeta prime, and we can use these two terms, r by sine delta zeta and d by sine zeta prime, to figure out that sine delta zeta is equal to r sine zeta prime divided by d. So, this is the observed zenith angle, and this is what the effective correction for parallax would be. So, in summary, the observed positions of solar system bodies need to be corrected for parallax, or where the observer is with respect to the center of the earth. All the calculations for positions are done with respect to the center of the earth, but they need to be corrected for where you are sitting. Now, the geocentric parallax is going to move objects away from the zenith towards the horizon. It is going to make things look further down than they actually are, and it changes as the earth rotates, or equivalently as the objects rise, transit and set. The parallax which you get is the sine inverse of r sine zeta prime by d, where zeta prime is the observed zenith angle, and for far away objects this can get simplified, because sine inverse of a small quantity would be the small quantity itself, and zeta prime will approximately be equal to zeta. So, for far away objects, delta zeta is equal to r sine zeta by d.